I thought it was interesting.
Oh, man, I didn't know.
You didn't know that?
Yeah,
I thought so.
Most sensitive thing ever.
Michael? It's called touring to the beach. It's about the students. I was surprised that Jim Wilkins was not making So, yeah.
was it about the US though?
Yeah. Oh, hi. Michael. See you at 6.
Oh, no, right there. Remind
I'll remind Alan too.
Yeah, and it was Oh, I know. I played with him years ago when I played. I know. I think our mayor is giving his talk.
And it's 4:15. Does that mean we should start?
So this is Stephen Boyd's
All right.
seminar.
Well, welcome to ISL Colloquium. We have Mr. Mackey all the way from over in the Stat building. So your flight was okay? So he's here as a strange situation, right? Because you're a postdoc now, but a faculty member next year? That's right. Okay. All right. So I guess that's better than the other way around. It's great. It came by way of Berkeley from Michael Jordan's group, and before that from Okay. So we'll talk about matrix completion and matrix concentration. I guess that's just in the air these days.
All right, thanks. Thanks everyone for coming. This is going to be a talk in 2 parts. So in the first part, I'll introduce divide, factor, combine, which is a parallel divide and conquer framework for either large-scale or real-time matrix completion. And we'll see that the analysis relies heavily on these concentration inequalities for random matrices. So in the second half of the talk, I'll show you some techniques based on Stein's method for shaped from exchangeable pairs for deriving those sorts of concentration inequalities. All right, let's start with part 1. So the motivation of this talk is going to be large-scale matrix completion. So say you're given a bunch of entries from a matrix. We'll call it matrix L naught. It's an m by n matrix. And your goal is to basically estimate or recover all the missing entries of that matrix. So where does this come up? A pretty common example is the collaborative filtering problem. So you observe a bunch of ratings that different users gauge different movies, and you like to predict how they'd rate other movies in the hopes of recommending movies to them in the future. And if you're a company like Netflix, you'd like to do this at scale. So you might have 10 million users and 100,000 movie titles, and you'd like to basically complete this entire matrix, this very large matrix. As a second example, if you're a company like Google News, you may have millions of articles and millions of users both shifting on a day-by-day basis, and you'd like to predict what articles a user would like to read in the future based on his past reading habits. Okay, again, a big matrix completion problem. And just one final example, a link prediction problem. So you might observe on a social network that these people are friends with these other people, and you want to predict who else they're friends with. You want to predict those links between individuals. And in a case like Facebook, you have over 500 million users. This is, again, a very, very big matrix. So what does the state of the art look like? So this problem is now a well-studied problem, and we have lots of good algorithms that have strong estimation guarantees. They say that I only need to see this small fraction of the entries in the matrix before I can complete the entire thing. Those are very good guarantees. But these algorithms are also often plagued by expensive subroutines. So So they may have to compute a truncated SVD on every iteration of a gradient descent procedure, making them very, very expensive. Very, very expensive procedure. So this talk is about combining scalability with strong estimation. How can we take a given matrix completion algorithm and scale it up to one of these very large-scale problems while still maintaining the strong estimation guarantees? Okay, so this is the goal as I first stated it. An exact matrix completion problem, we actually see entries of a matrix, L naught, and we want to complete that matrix. In reality, we often have a noisy problem, right? We don't actually see the entries of the matrix we're trying to recover. What we see is entries of a matrix M, where M is L naught, the thing that we care about, plus Z. Z is just noise on every entry. And we still want to estimate L naught. So in general, this is a completely ill-posed problem. If I give you an arbitrary set of entries from an arbitrary matrix, you have no hope of recovering it. And so in practice, we need to make some sort of structural assumption. So the assumption that we'll make here is that L naught has a small rank. It has a rank R that's much less than the ambient dimensions M and N. Okay, so why is this a good idea? Well, if L naught has small rank, it actually means that it has many fewer degrees of freedom. You can actually write L naught as a product of two lower dimensional matrices, A and B here. And it only has about M plus N times R degrees of freedom, even though there are Mn parameters altogether. And that's good. That means that somehow we expect that we can see only a subset of the entries of L naught and still recover it. So that's a good thing. The bad news is that even with this assumption, this low rank assumption, we can't possibly hope to recover any matrix. Something can still go wrong. And so the question might be, what can go wrong in this problem? So this is one thing. Perhaps imagine that you don't sample any information about a given user. So I know nothing about that user's preferences. Then if I ask you to recover its preferences, you basically have no hope. Even though this could potentially be a very low rank matrix, there's no way I'll recover anything about that user. So we need some way of getting rid of this sort of situation, and there are various ways of doing that. The assumption that we'll make for this talk is that we have a uniform observation. So that is, when we see entries in this matrix, we're essentially sampling them uniformly at random across the matrix. This is not the only assumption you can make. We can relax this a bit. We'll use this for the talk. So we'll call the set of entries that we observe here omega, and we'll say that we observe S of them, and they're uniformly distributed across the matrix. Okay. Another problem is that you could have a bad spread of information in your matrix. So see, up here I have an example matrix L. It's 3 by 3. Imagine it's a million by a million, and that it has only a single 1 entry. All the other entries are zeros, but it has a single 1 up in the top left corner. And if you don't sample that single entry, then there's no way you're going to recover it, right? The best guess for the entire matrix is that it's all zeros. And the problem here is that most of the information in the matrix, in fact, all of it is just single entry. And that it's not spread out across the matrix. So again, we're going to need some sort of assumption to avoid cases like these. The assumption that we'll make here is a pretty standard one these days. It's this incoherence assumption for standard basis. Now, I've written down exactly what that means here for rank R matrix. It's expressed in terms of the singular value decomposition of that matrix. So imagine that the matrix L has a singular value decomposition U sigma V, V transpose. Then basically the assumption says that the singular vectors are not too skewed and not too cross-correlated. There is a very specific assumption here. The details of that are actually not incredibly important for the talk. But the key idea is that singular vectors are not too skewed, not too cross-correlated, so we're avoiding situations like this, where all the information is concentrated in a single vector. Okay. And if anyone has any questions, actually, as I go along, you should feel free to ask. Okay. So that's about all that can go wrong. And now the question is, how do we go about estimating this matrix L naught? Well, the first thing you might think of doing is, we'll find a matrix with the smallest rank that matches the entries that we've seen. So if I sample a bunch of entries from L naught, then that would be a reasonable thing to do, perhaps. But remember that we are in this noisy setting, so we don't actually see entries of L naught. We see noise-perturbed versions. So we're going to add some slack here and say that we want the lowest ranked matrix basically within delta of the entries that we've seen, where delta is some sort of upper bound of the noise. Okay, so this is a reasonable thing to do. We know our matrix is low ranked. We know some entries, up to noise. But of course, this is a computationally intractable problem. We can't actually solve this, well, in general, because it's NP-hard. So what can we do? We can solve a convex relaxation of this. This is a pretty standard thing to do. Instead of minimizing this rank penalty, we'll minimize a trace norm penalty. That's the sum of the singular values of our matrix A. And that means that this is a convex relaxation. It's a convex program. We can solve in polynomial time. questions that remain are, well, is this a good thing to do? Will it actually recover the matrix that we care about, L naught? And is it scalable? Will it actually extend to the problems that we care about? Let's go through each of those questions. First, this heuristic, it's often called the nuclear norm heuristic. Does it work? Does it give us back the L naught that we care about? Well, it turns out that yes, it does work. You can show that it actually holds with high probability. And here's the kind of theorem that you'll see in this literature. So L naught has rank R, and it's incoherent, meaning it has a good spread of information. Then you can sample about Rn log squared n entries, and use this nuclear norm heuristic to solve the problem, and get back a guarantee of this norm. So if your noise level is delta, then your recovery error is now scaling with delta times some function that really depends on the analysis that's being used. And you can see a variety of different results of this flavor. One interesting thing that comes out of this particular result as stated is that you actually have exact recovery here. So if your noise level your problem is 0, delta is 0, then you actually get exact recovery L naught, even though you've only seen a small subset of the entries. And otherwise, your error level will scale with the noise level. Okay, so that's good, it works. But now we have a question of, does this scale? Can we solve this problem in a scalable fashion? And well, what we see is that, okay, well, first we know that we can actually solve this problem with standard interior point methods. We can actually represent it as a semi-definite program, use standard interior point, but we get what's actually pretty bad scaling in terms of the parameters of the problem. But we don't have to stop there. I mean, there are many more efficient algorithms that we could use to solve the problem, and many have been designed. Some of the earliest ones are singular value thresholding, augmented Lagrange multiplier method, accelerated proximal gradient. These are all much, much faster than interior point, but they all have a common requirement. That is, they require these rank k, in the best case, rank k truncated SVDs on each iteration. So there's iterative procedures with multiple rank k truncated SVDs. So still not very scalable. The takeaway here is that these provably accurate MC algorithms can often be quite expensive actually to solve on large-scale problems. And a question that we might have is, how can we scale up a given matrix computing algorithm? Say you have your favorite one. It has certain guarantees, it has certain properties that you like. How can we scale that up and still retain its estimation guarantees? Okay, so here's one solution. Divide and conquer. It's a pretty simple idea. It's going to have 3 steps. The first step, we're going to take our original input matrix M. Remember that we don't actually see all of M, we just see some of the entries, so this is what this projection onto the set omega means. We see the beginnings of M. And we're going to divide it into a bunch of column submatrices. We're going to complete each of these submatrices in parallel. So we're going to get back estimates C1 hat through CT hat. And then we're going to have a certain way of combining these estimates using techniques from randomized matrix approximation. And we're going to use that as our final estimate of L naught. Okay, so those are 3 steps: divide, factor, and combine. All right, so what's the advantage here? So the main advantage is that submatrix completion, using a much smaller submatrix, is often much cheaper than completing the entire chain. This is where we'll get most of our speedups. Since the submatrix completions can be carried out in parallel, we're actually only paying the cost of the most expensive one. You can actually apply this to any base algorithm, so it could be the ones that we've discussed so far that have these nice guarantees. It could be another one that just happens to be your favorite algorithm. And also, with the right choice of division and recombination, we can actually obtain estimation guarantees that are comparable to the original base procedure. Okay, so I'm going to go through each of these steps in a bit more detail. All right, step 1. We take our matrix M, and we're going to randomly partition it into T column submatrices. So the original matrix was M by N. Now each Ci is going to be M by L, where L is N over T. Now we're going to complete each of the submatrices in parallel. So we're going to get back an estimate for each one. We call those C1 hat through CT hat. Here we get a reduced cost. So we expect maybe a T-fold speed up per iteration if we're counting for K truncated SVDs. And we can also, since we're using parallel computation, we're only going to pay the cost of one cheaper submatrix completion. All right, now we have a third step. So what do we get back from these algorithms? So we have all these submatrix completion problems, all these CI hats. Each one tends to be low rank because of the sorts of procedures that we're using. But each one might be capturing a slightly different column subspace. So now we want one final low rank estimate of our matrix that takes into account these different subspaces captured by the submatrix properties. So essentially, we need an estimate of the column space of L naught. And one simple way of doing this is to estimate it using the column space of one of our areas, one of our submatrices. So we can imagine using the subspace from C1 hat and projecting all the other matrices onto the column subspace. This is a pretty common technique that's used in randomized low-rank approximation when you don't have the completion problem. So if you start with a complete matrix, this gives you a cheap way of computing a low-rank approximation to a complete matrix. And in our case, it's very cheap, because each of these submatrices, Ci hats, are going to be in factored form, which means that the cost of doing this whole projection is only mk squared plus lk squared, which is much, much cheaper than step 2 doing the completion. Now this works quite well if your noise level is pretty small, but we find that in practice, a secret fourth step helps, which is ensemble. So instead of just projecting onto the column space of C1 hat that's somewhat arbitrary, we project onto each of them, and then we're averaging estimates. Okay. So does this work? It seems somewhat clear that we'll get some sort of speed up, but does it actually give us back any nice sort of estimation guarantees? And what I'll show is that, again, yes, with high probability, we can get estimation guarantees comparable to the base algorithm. So again, under the same assumptions, if L naught is rank R, it's incoherent, it spreads information. And now we need slightly more entries. We need R squared here instead of R, but R squared and log squared n entries. Then we get back a guarantee like this. So again, delta is our noise level. Before we had, for the base algorithm, this function f times delta. Now we're getting basically a 2 plus epsilon slack in our error. And basically this is saying that the more entries we sample, the better our error guarantees. And we can do all of this by sampling only a sublinear number of columns. Oh, yes.
One question. So you said in the previous term that the f depends on the analysis.
That's true.
Now you get the factor 2 with respect to which analysis?
With respect to a couple of different ones. So I mentioned a few of them on the earlier slides. This one by Candace and Plan for the noisy case. That's one case. Another is with respect to the analysis of the Negaban and Moonlight, which uses a slightly different set of assumptions, but it's the same sort of format. Basically, you can push through a lot of the different guarantees because essentially you have used this group. Right. An interesting fact here is that you can actually sample a sublinear number of columns, which is the key takeaway here. That as n grows larger, you can actually sample a vanishingly small fraction of the columns and still get good error guarantees. And again, if delta is 0, you get exact completion, which is a nice thing because then now this 2 plus epsilon doesn't matter anymore when delta is 0. So we get exact completion even by doing essentially less work. And the analysis of this relies heavily on these matrix Bernstein inequalities. That is a matrix extension of the classical Bernstein inequality, which I'll talk a bit more about. I'll talk about that a bit more in the second half of the talk. Okay, let's see this in practice. So first I'll show you some simulations. So the x-axis here is the percentage of revealed entries in randomly sampled low-rank matrices. The y-axis is the mean squared error, so the recovery error. And the black line represents the error of the base algorithm. These two blue lines represent the DSE algorithm that is presented with only 10% of the columns in each submatrix. So we have 10 submatrices. The dotted blue line is before doing that ensembling step, so using just the first 3 steps, and the solid blue line is what you get when you add in the ensembling. And you see that after ensembling, we have a breakdown point that's earlier than the base algorithm, but by the time we get to about 2% revealed entries, we're essentially recovering the same error, even though we're saving a lot in terms of computation. And as the matrix size grows, here we're using 10,000 by 10,000 size matrices, both of these breakout points push farther and farther down. So here's the timing plot for the same algorithms. Again, the black line is the base algorithm, the blue line represents this DFC, this divide factor. And you can see that the scalability is just much better as n grows larger. Okay, so let's look at this on real data. So here's a task, collaborative filtering, use it to motivate the problem. So we're given a sparsely observed matrix of user item ratings, and we want to predict the unseen ratings. So some issues here. Of course, this matrix is not exactly low rank, but we hope it's well approximated by a low rank matrix. And we also have very non-uniform observation patterns, but we're still going to follow ahead. The data we'll use is from the Netflix prize data set. So we have, in this case, 100 million ratings between 1 and 5 stars, about 18,000 movies, and about 500,000 users. Okay, so here's the performance of a base algorithm. It's an accelerated proximal gradient algorithm. I should say that this is on a random train test split, so you can't really compare these RMSEs to the contest RMSEs, so don't get too excited. But this RMSE of this algorithm is about 0.8433, and it takes it about 2,600 seconds to get to that answer. Okay, so this is what we're seeing with DFC. So with DFC, if we divide our matrix into 4 column submatrices, we get nearly the same performance in about a quarter of the time. Into 10 column submatrices, we get slightly higher performance in about, with about a 9x speed up. Now this is all before ensembling. So if we do ensembling, we see first that the timing hasn't really changed, because the ensembling step is actually quite fast compared to the other steps. But even with 10% sampling, we're getting the same error as the base algorithm in about 1/9 of the time. Yes, in the 25% we actually get slightly better error. We don't have a good explanation for that, or very good. That's also true. Okay. I just want to show you one other example. It's not matrix completion anymore, but it still fits into the same framework that we're trying to recover a low-rank matrix, and we like to do it at scale. So this is what we're called the robust matrix factorization problem, or the robust PCA problem, it's often called. Here you're given a matrix M. It's the sum of a low-rank matrix plus a sparse matrix, and you want to recover the low-rank matrix. So here you might see the sparse matrix is an outlier or a corruption matrix that could essentially perturb your column space if you were just to use something like PCA. And so you need to make a method that's actually robust to sparsity that's potentially very large in magnitude. So here's one problem that's often used to motivate this formulation. So imagine that you have security footage. You have security footage, you have a video, a series of images. Take each image, you vectorize it as a single column in a matrix, and you consider 2 components of that vector. You have the background, which is basically static over time, that's the low-rank component, and then you have people walking in and out of the image trying to get the sparse image. Okay, so this is a bit harder than matrix completion because you could also view matrix completion in this framework. I have the low-rank matrix plus my outliers, the entries that I haven't seen. But you know where those outliers are. In this problem, you don't actually know which entries correspond to outlier matrices. And it's actually even more expensive than a matrix completion problem because now we have dense, fully observed matrices, whereas at least we could leverage sparsity in the matrix completion system. I just want to drive home that last point. Here's a timing plot of randomly sampled robust matrix factorization problems. And you can see that once we're at 2,000 by 2,000 matrices, it's already taking this standard algorithm, this accelerated proximal gradient algorithm, about 10,000 seconds to recover its solution. And you can see that the scalability of our DFC algorithms is much better. Okay, so I want to show you an example of the kind of output you get on this problem using DFC. Exactly on this video background modeling challenge. So you have your matrix M again, you have images from a video, you're going to take each video and make that a single column of a matrix, and you want to separate the video into its background and its foreground. Okay. On the top left here, you have the original video. On the top right, you have the background that's extracted by the full base algorithm, so the full RMF algorithm. On the bottom left, you have the background extracted by DFC, and the bottom right, you have the background extracted by DFC plus that ensemble. And basically, what you want to take away from this is that the reconstructions are essentially the same, even though the ones in the bottom are taking much less time to compute. You see people moving through, there's that one guy who's standing there for a while, so there's part of the background. But then he moved away. Okay. Back to the slides. Yeah, exactly. always Okay, so I'm actually going to end the first part at the top there. I'm going to move to the second part, which is Stein's method for matrix concentration. All right, so when I talk about a concentration inequality, I mean a quantity like this. It's a scale down. Oh, sorry. Yeah, question.
In that first part,
Yeah.
the ensemble method that you use isn't necessarily going to return a sparse a low-rank matrix. Then.
That's right. So what we actually do is take the average and then so each of those submatrices itself has a rank. So we choose the largest of those ranks and find the best rank K approximation to that ensemble.
Okay, thank you.
Yeah, that's a very good question. Yeah.
Does the ensembling give you better theoretical guarantees?
No. So at best we have the same guarantee for the ensemble. It would be nice to know or to prove that in fact that it does help. Because it really seems to help. Any other questions? Okay. All right, part 2, matrix concentration. Okay. So we'll be interested in inequalities of this form. So tail bounds that are controlling the deviations of a random variable from its mean. In particular, we're interested in the matrix analogs of these. So again, a tail bound that controls the fluctuations of a random matrix about its mean. We need some way of measuring that, so it might be in terms of the matrix norm, or perhaps an eigenvalue if eigenvalue is defined. And we care about these because many matrices have complex structured distributions that are difficult to characterize exactly. And so we want a technique that gives us convenient, non-asymptotic control of these random fluctuations. Okay, and so these sorts of inequalities have already found a variety of applications. So they're actually fundamental to the analysis of these matrix completion procedures from sparse random measurements. Also quite useful in establishing guarantees for randomized matrix multiplication and factorization. They found use in the convex relaxation of difficult, robust, and chance-constrained optimization problems. And they also have been heavily used in randomized random graph analysis. Okay, so what's the difficulty here? So why is it hard to establish a guarantee like this, or to establish a concentration inequality like this? Well, the main difficulty is that matrix multiplication is not commutative, which means that known truisms like e to the x plus y equals e to the x times e to the y just aren't true anymore. And there have been some past approaches to dealing with this difficulty. A lot of them rely on these deep results from matrix analysis, like Goldman-Thompson's inequality or Lewis' concavity theorem, and they apply to sums of independent matrices and matrix marking units. So here we're going to take a very different approach. We're going to use Stein's method of exchangeable pairs as advanced by Sharov-Chatterjee for scalar concentration. And we're going to get some improved exponential tail inequalities. I'll show you an optimal matrix-Hoffman inequality that comes out of this analysis. We'll get some polynomial moment inequalities of the Khinchin and Rosenthal varieties. And we'll also have extensions for dependent sums and more general matrix functionals. All right, so here's the outline of the rest of the talk. I'll give you some background into Stein's method and some notation, and then I'll present some exponential tail inequalities, then polynomial moment inequalities, and then I'll just go through a list of some different extensions. All right, so some notation for the talk. So from here on in, all matrices are going to be Hermitian, so they're complex D by D matrices that equal their conjugate transpose. This is useful because they have real eigenvalues. I'll use lambda max to represent the maximum eigenvalue of a matrix. We'll be using the trace of a matrix quite often, which is the sum of the diagonal entries of the matrix. And the spectral norm. This unadorned norm will represent the spectral norm throughout the talk. That's the maximum singular value of the matrix B. Okay, that's all the notation. So let's consider. So this is a talk fundamentally about exchangeable pairs. What do I mean by that? A pair of random variables, z prime, is exchangeable if z prime is equal in distribution to z prime z. And we'll be interested in a specific class of exchangeable pairs, which we call matrix Stein pairs. So imagine that you have a function psi that maps from the range of z into the space of Hermitian matrices. We'll apply that function psi to z and z prime. We'll get back a pair of matrices x and x prime. And we'll call xx prime a matrix Stein pair if it satisfies this conditional equality. So the conditional expectation of x prime given z is equal to a multiple of x. In particular, it's equal to 1 minus alpha times x, and that alpha has to be somewhere between 0 and 1. Okay? A couple of facts about these matrix Stein pairs. First, they themselves are exchangeable pairs because z and z prime are exchangeable. And they always have 0 mean because of this conditional expectation condition. All right. So we're going to associate with each of these matrix Stein pairs a special matrix. We'll call it the conditional variance. And the conditional variance is essentially the expected square difference of x minus x prime conditioned on z. It's basically that rescaled by this 1 over 2 alpha factor. Okay, so let me just get some intuition for this. Basically, this is a stochastic estimate of the variance of the matrix X. In fact, if you were to take the expectation of delta X, the conditional variance, you just get back the expectation of X squared, which is its variance. And this is actually a very important quantity. This is probably the most important quantity that we'll encounter. In fact, if you take away nothing else from the rest of this talk, this will be the thing to take home, that control over delta X, control over the conditional variance, gives you control over the maximum eigenvalue of X. If delta X is small, then basically the maximum eigenvalue of X is going to be small. And everything that I do from after this will be controlling this quantity. Okay. Let's see what we can do with this. So here's a pretty general concentration result. So imagine that we have our matrix Stein pair, XX prime. We care about this matrix X and controlling its concentration. And imagine that we have a linear upper bound on the conditional variance delta X. Then you can establish a tail inequality like this that looks a lot like a Bernstein-Tail inequality. In particular, you have a Gaussian tail for small t and an exponential tail for large t. And the rate of decay is controlled by these two parameters v and c that appear in this upper bound on the matrix delta X. Okay, just a couple of points about this. So you have this d factor sitting out in front. You don't typically see that in scalar concentration. When d equals 1, you just get back a scalar result due to Chatterjee. But in general, you can't get rid of this d-dimensional dependence. There are special cases when you can, but you need it in general. Okay. So I'll give you one consequence of this. So you can actually use this to establish a matrix version of the Hupting inequality. So imagine that you now have a sequence of random matrices. Each is mean 0. They're all independent. We'll call them yk. We'll index them by k, so they're yks. And imagine that each one is bounded, and which in this case means that yk squared is upper bounded by some ak squared, which is determinism. You can define a variance parameter, which is just the spectral norm of the sum of the bounds squared. And you get back what looks exactly like the Hupting inequality, except you have this variance. So you can control the maximum eigenvalue of this sum of independent matrices with a Gaussian tail that depends on this variance parameter signal. There's actually, so Joel Trop had a matrix Hupting inequality in some earlier work, which used a very different path of proof. This actually improves upon this. You actually get the optimal constant at 1/2 here. I think you have 1/8 in that result. Another interesting fact is that it just kind of falls out of the analysis, is that you can replace this typical upper bound, the sum of the squares of the bounds, with the mean of the bounds and the variances. So you actually get a slightly tighter bound there. In fact, it's even tighter in the one-dimensional case. Okay, so this is the sort of thing that you can get out of that general result in the past slide. I'm going to be a bit ambitious and try to prove that result for you. But, there are only 4 steps. I'll try to make them brief. And the first step is what you might call the matrix Laplace transform method. So this is originally due to Alzwedder and Winter. And it's a really good idea. It gets intuition from the scalar setting. So in the scalar setting, how do we get exponential concentration for random variables? Well, we take our tail bound, we take our probability, and we relate it to the moment generating function of the random variable x. Okay, so we want to do something similar in the matrix setting. In this case, we relate the tail bound that we care about, the probability, to the trace generating function. So the moment generating function itself is a matrix, so we need to relate to some sort of scalar quantity, so we'll take the trace of it. So the trace MDF here we'll call m of theta for each value of theta. Okay, now this is where the difficulty comes in, because in the scalar setting, if we had to say a sum of independent matrices, we would just decouple the exponential. We would say that e to the x plus y equals e to the x times e to the y, and all those terms would be independent, and we basically would be done. In this case, that's just not true anymore, because our matrices are not commutative. So past approaches for dealing with this have, as I said, appealed to different results in matrix analysis. We're instead going to extend Chatterjee's strategy for scalar concentration So what's the idea? We're going to control the growth of this MGF, m of theta, by bounding its derivative. The derivative looks like this. It's m prime of theta. It looks like the expectation of the trace of x times some function of x. And it turns out that using exchangeable pairs, and in particular using these matrix Stein pairs, we can always rewrite this expression in a more convenient form. So this is going to be step 2, what we call the method of exchangeable pairs. So imagine that you have a function of this form, expectation of x times f of x. Then using exchangeable pairs, using a matrix Stein pair, you can always rewrite it in this form on the right-hand side. So now you have an expectation of 2 differences. One is x minus x prime, and the other is f of x minus f of x prime. And what's the intuition? Well, often to characterize a distribution of a random variable or a random matrix, you can integrate it against a class of test functions. So you can view f here as a test function. And this is letting us estimate the integral on the left-hand side using the smoothness properties of f and the difference between x and x prime. This basically tells us that when we construct our matrix Stein pairs, we want to pick a pair of exchangeable matrices that are essentially pretty close together. Okay, so let's apply this back to our proof. So this was our derivative of the trace MGF. We can rewrite it using the method of exchangeable pairs. That's step 2. Now we want to somehow use the smoothness of f of x to bound this derivative. So f of x here is e to the theta x. Yeah.
How is x prime constructed? You didn't give us that.
I haven't told you that. It actually depends on the result that you want to get and the matrix x that you're trying to analyze. In the case of the sum of independent random matrices, imagine that you actually have now a big vector of those random matrices. You pick one at random, you throw it away, and you replace it with an independent copy. That gives you something that's exchangeable, but it's also pretty close to the original, because you're only throwing away one matrix. And actually that trick of basically throwing away one and resampling it works in a lot of different cases. But what I'm proving is actually a general statement for any pair of exchangeable matrices. But it might not be very clear if you read that. Okay, so how do we use the smoothness of e to the theta x to bound this derivative? So we need one more piece of notation. So imagine that you have a real valued function g. It's maps from R to R, and you want to extend it to matrices. Well, you can take your matrix, write it in its eigenvalue decomposition. So q are the eigenvectors of A, lambdas are the eigenvalues. And you can define a function g of A by just applying g to each of the eigenvalues. Right, and this is what we call standard matrix functions. So the same eigenvectors, just transform the eigenvalues with them. Okay. So we're going to be interested in a particular pair of these standard matrix functions. So we have one function g that's weakly increasing. We have another function h that has a convex derivative. And we care about bounding an expression like this. The trace of g of a minus g of b times h of a minus h of b. And it turns out you can always rewrite this. So you can actually keep g of a minus g of b the same, and you can replace this h difference with a minus b times the average of its derivatives at a and b. Okay, and it turns out that this is what you would expect in a scalar case. If everything was a real value, you expect this sort of equality. Here, you need the trace to make this work. And the way we'll apply this is by using g of a equal the identity, so g equal the identity function and h equal the exponential function. So let's plug this back into our proof. So here's the expression that we had for m prime of theta. Now we use this mean value trace inequality to get an upper bound on m prime of theta in terms of these exponential functions and now the square difference between x and x prime. And now we can use exchangeability because we have an expectation here and we have a sum of 2 terms. And they're the same except for one uses x and one uses x prime, which means they're actually, because they're exchangeable, they have the same distribution. So we can actually throw one of those copies away. This is what we're left with. And we'll just do some reorganization of the terms here, and what we get is this matrix delta x that I was talking about earlier. So if I express that in, what we have is an upper bound on the trace MGF, the derivative of the trace MGF, in terms of delta x. Okay. So that's step 3, and now all we have left to do is to plug in our bounds. We have an upper bound on delta x. It's in terms of a linear function of x in the identity matrix. So let's plug that in. Plug it in, and what we have is a differential inequality. On the left-hand side, we have m prime of theta. On On the right-hand side, we have other terms that are m prime of theta and m of theta. We can solve that differential inequality, and that's what actually gives us the upper bound term here. And we'll go through the algebra that just directly gives you. That's the first. And a similar sort of proof actually gives rise to a different flavor of inequality. So say that instead of being interested in tails, you're interested in moments. So say you wanted the pth moment or the 2 pth moment of the matrix X. Well, you can actually upper bound that in terms of the pth moment of your conditional variables. So that's what this inequality says, that the moments of X are basically upper bounded by the moments of conditional variance matrix. And this actually gives you a generalization of Chatterjee's scalar for Coulter-Davis-Gunn inequality. And there are other ways of establishing these sort of results. There are a variety of ways that have been around for decades, in fact. In this case, the proof techniques are very much like the exponential concentration proofs that I just gave you. And it's interesting that the same result, although the exponential concentration depended on that factor d, which represented the dimension of your matrix, here the results also extend to infinite dimensional operators pretty directly. So let's give you one consequence of this result, a matrix kinship inequality. So here, let's say you have a Rademacher sequence of independent plus or minus 1 variables. Okay, they take both values with equal probability. And then you also have a deterministic sequence of matrices. And let's say that you're interested in the moments of the sum of epsilon k a. Well, it turns out that you can just bound that in terms of the sum of the ak squares. And this is not a new result. It's been proven by many individuals at different points in time. But it has been a dominant tool in matrix analysis. So it's been used for instance, analyzing random column sampling and randomized SVD by rule 70%. And it turns out that Stein's method gives you an unusually concise proof of this result. And this constant here is actually known precisely. This has been studied to death. And in this case, it's about off by a factor of root b. Okay. So what else? So I don't have time to go through all of the different applications of this, but I'll mention a few briefly. So first, you can get refined exponential concentration. So we actually have a result that relates the trace MGF of a random variable directly to the trace MGF of delta x, the conditional variance. And that gives rise to a Bernstein inequality instead of a Hopf inequality. And this also gives you tools to deal with unbounded random matrices, whereas everything I've talked about has essentially been bounded. Now, I've also restricted our view to Hermitian matrices, but that's actually not a very substantive restriction, because you can always map a general matrix into a Hermitian matrix. So imagine that now you have a general complex D1 by D2 matrix. You can embed it in a Hermitian matrix using a technique called dilation. It just looks like this. Put B in the upper right corner, B transpose or B conjugate transpose in the lower left. And that's Hermitian. And the maximum eigenvalue of this dilation is equal to the spectral norm of B. So if you can use these tools to get control of the maximum eigenvalue of dilation, then you can also control the spectral norm of a general matrix. And finally, the same techniques extend to dependent sequences, so you can treat, for instance, sums of conditionally mean zero random matrices, combinatorial matrix statistics that depend on random permutations, and also matrix value functions that satisfy self-reproducing property. And this actually gives rise to a matrix version of the bounded differences interval. Okay, that's it.
We have time for questions. Oh, yeah. So I stated it that way in some sense for ease of statement. We have a bound in the version between as well, but it's different by a factor of 2. Oh, the D. So you can often replace that with a different quantity that looks more like the ratio of 2 norms of your matrix X, which is
Yeah, so, sorry, sorry, it's a ratio of the expected value of a variable. So, like the ratio of the Frobenius norm to the trace norm, or ratio of the trace norm. You can usually get away with one of those two quantities, and that could have nice properties. For instance, if X was low rank, you get a factor of R rank. I think you can do a bit better in certain cases. For instance, if you know something about the structure of your matrix, so this is sum of independent matrices, and each of those matrices has rank R, then in some cases you can actually get a factor of R there as well. In some cases.
In many proofs of all these Hanna reduction theorems, you prove by maybe the spectrum of the next mathematics. So can you do this proof using this trace estimate? Because then you can extend it into three-dimensional space.
I'm not sure. So what do you want to redo? So instead of the spectral norm and the tail down, you want to use...
Right. You use a truth
Oh, so use the moment inequalities.
Yes, the moment inequality.
That's true, but you still have it's still. So all it does is related to the conditional variance, and you still need to bound that conditional variance. So if you were then to try to derive the same tail inequality by bounding conditional variance, then the factor of problem fails.
In the first part, you mentioned that L is incoherent that matrix. And does that mean it's high integer matrix?
So incoherent in this case actually means that the values don't fluctuate that much. So there are different ways of quantifying that, but it's basically trying to move away from the case where some part of the matrix has very large values and the rest of the matrix has very small. Another assumption you can